We're examining the conservation of potential vorticity, and we've just been through the process of deriving the planetary Rossby wave equation, which describes the organization of small perturbations into larger, coherent fluctuations that ride on top of the background geostrophic flow. These planetary Rossby waves arise because of the latitudinal dependence of the Coriolis parameter f, which we can linearize with the beta plane approximation. Planetary Rossby waves are responsible for much of the weather that we experience at mid-latitudes, and perhaps the best known example of these waves are the regular latitudinal fluctuations in the location of the jet stream, the strong eastward winds that blow in the upper atmosphere over North America, Europe, and Asia. Our derivation included integrating the continuity equation over some layer depth h and substituting into this the geostrophic plus ageostrophic horizontal velocities, where the pressure terms have been expressed in terms of eta, which are small perturbations on the free surface height, and where this term r, which we call the Rossby radius, is given as the square root of gh on f0. This derivation gives us the rate of change of eta minus the Rossby radius squared times the rate of change of the Laplacian of eta minus the Rossby radius squared times beta times the x derivative of eta. Here we will look into the dynamics described by this wave equation. Recall that we can consider the small ageostrophic perturbations as a wave with zero time mean component. This allows us to give them the form of eta equals some reference eta times the cosine of kx minus my minus omega t, where k and m are the zonal and meridional wave numbers, respectively, and omega is the wave frequency. Assuming this form allows us to rewrite the Rossby wave equation in terms of omega, giving us a dispersion relation for planetary Rossby waves, so omega equals to the negative of beta times the Rossby radius squared times k on 1 plus r squared outside of k squared plus m squared. Now let's take a look at what this dispersion relation is telling us about the frequency of planetary Rossby waves. First of all, for beta equals 0, omega equals 0, and we have no travelling waves, just steady geostrophic flow at constant f. That is, planetary Rossby waves require a spatial change in f. Now we have assumed that the Rossby number is small, that is, the wave speed of the perturbations are small and or the wavelengths of the perturbations are large. Either way, this means that the solution is only valid when the frequency of the perturbations, omega, is much smaller than the frequency of Earth's rotation. Now if we think of k, m as 1 on L, some length scale, it follows that the perturbation frequency omega will go as beta times the Rossby radius squared times the length scale L on L squared plus R squared. This means that for short waves, where L is much less than R, omega becomes beta L, and that for long waves, where L is greater than R, omega becomes beta R squared on L, which is less than beta L. Interestingly, this also suggests a maximum in the frequency for L is the Rossby radius, a maximum frequency of beta R on 2. Perturbations at higher frequencies than this are unable to directly excite planetary Rossby waves. Now let's consider the propagation of planetary Rossby waves. The zonal phase speed is omega on k, which is negative beta r squared, 1 on 1 plus r squared outside of k squared plus m squared. Now there is no way that this can be positive, which means the zonal phase speed of Rossby waves is always westward. Remember that these waves are small perturbations about the geostrophic flow, that flow which can be eastward and faster than the zonal phase speed of Rossby waves. So the planetary Rossby waves can be blown eastward by the background flow but they themselves are always propagating westward. There is no such constraint on the meridional phase speed, meaning the waves can propagate westward between northwest and southwest. The very longest waves are those that have the maximum phase speed, which approaches beta times the Rossby radius squared. Remember that this speed can still be much slower than the background flow speeds. Let's have a quick look at the physical implications of this derived wave equation. Picture some point on Earth where you have a gradient of f from low f in the south to high f in the north without any change in h. Now imagine a stream path that follows along some contour of f. Picture that the stream path is perturbed in some way, and that the perturbation can be described as a wave, taking some portions of the flow into regions of higher f and some portions into region of lower f. In regions where the stream path has moved to higher f, the fluid on the stream path will reduce its relative vorticity so as to maintain potential vorticity. In doing so, it will be rotating clockwise relative to its surrounds. For fluid on the stream path that moves into regions of smaller planetary vorticity, to maintain potential vorticity, it will have to increase its relative vorticity and be rotating anticlockwise relative to its new surrounds. So that when we consider the net effect of these perturbations on the original stream path, we can see how they tend to promote a westward propagation along that stream path.